Hello, everybody. My name is Masood Olia, and I'm a professor in the School of Engineering at Wentworth University. And I'm here with another problem related to the topic of rigid body equilibrium. It's a three-dimensional problem, as you can see. And let me move this in. And obviously related to the subject of statics. So let's look at the problem statement. So we have a 100-pound door, which is being supported with two hinges at A and B. So it's a uniform, basically, door. So the weight will go right through the center of gravity. So I'm going to put my weight here. I'm going to draw the free body diagram of this guy. So 100 pound right through the center. And then if you look at the statement of the problem, it says determine the components of reactions at hinges A and B. If hinge B resists only forces in the X and Y directions, so hinge B only has components of reaction in X and Y. So one reaction here in the X, I'm going to call it BX, and one in the Y. I really don't know if these are the correct directions, so I'm assuming they're in the positive direction, and nothing in the Z. Well, it says A resists forces in X, Y, and Z. So in general, we'll say, okay, A has X component of reaction, a Y component of reaction, a Y, and A sub Z. So now the question is, how come we don't have any moment reaction acting on this at hinges? Because the hinges obviously are free to rotate about Z axis, so there's no moment reaction, but they can't rotate about about X axis or Y axis. That's true for both hinge at A and B. The reason for that is that these hinges are properly aligned. So when hinges are properly aligned or bearings are properly aligned, then the no moment reactions are developed, basically. So they're equal to zero. So here we have five unknowns, as you can see. And what will happen, we know that for a rigid body problem that is 3D, we have 6 equations. So what does that mean if we have 5 unknowns but only 6 equations? Or 6 equations but only 5 unknowns. That's what I meant, actually. That means that one of the equations is going to be useless, basically. And you'll see in a minute that that's going to be moment about z-axis. Now, let's start our equations. So basically, our equations for three-dimensional rigid bodies are 3 force equations that we have to satisfy, right? And 3 moment equations. You have to make sure that there's no rotation about x, y, and z. I mean, as you can see, we have 5 unknowns. So the question is, should I stick with my x, y, z the way they're shown here? No, you should move them actually to where it's more efficient. So I'm going to move them to actually my axis to x, y, to point A. The reason being that point A has the maximum number of unknowns, and by taking moment about the different axes at A, AX, AY, AZ clearly don't have any moment about that point. So let's do that. So I'll start with moment about x-axis at A. At A, moment about x-axis. So remember, what forces have moment about x-axis? Forces such as Bx, that is parallel to x-axis, cannot cause rotation, but By does. So moment of By, as you could see, is By times the distance to the x-axis, which is 48 inches. And the question is it a positive moment or negative moment? So this is where you have to use right-hand rule. So put your 4 fingers in use your right hand. Put your 4 fingers in the direction of By and try to rotate it about the x-axis. And you see your thumb points in the negative direction of x-axis. So this would be a negative moment. So you have to use the right-hand rule concept. And then on top of that, we have also the moment of the 100 weight about x-axis. That's 100 times 18, and this one is also going negative. If you put your 4 fingers in the direction of 100 in the negative z and rotate it about the x-axis, you end up getting a negative 100 times 18. So go ahead and divide 1800 by 48. Let's see, what do we get? 1800 divided by 48 becomes, I think I pressed the wrong numbers, becomes 37 and a half. So look, by happens to be negative 37 and a half pound. So that means the direction of by is wrong. So by should actually act. So I'm going to make it, put the correct direction of this guy here. I'll put it in a different color now that I've calculated it. So this is the by, which is now 37 and a half in the negative direction. Okay, so let's go to the next equation. Sum of the moment about y-axis equals 0, again at point A. So again, AX, AY, AZ are acting at A. They don't have any moment. So what's the moment of BX about y-axis? So again, that would be BX times 48 again, right? Using right-hand rule. So if you put your four fingers in the positive direction of, in the direction of BX and rotate about y-axis, you get a positive rotation. Your thumb would point in the positive y, along the positive y-axis, which is this. All right. Then look, the 100 passes through the y-axis. So it's not going to have any moment about the y-axis. And of course, the 37 and a half or by is parallel to y-axis, cannot cause rotation. By the way, you wonder what this 30 degrees is here. As long as you pick your axis along that the door edge, this 30 degrees is just useless. Actually, it's just to confuse you. All right. So the 100 doesn't have any moment. It passes through the y-axis. Therefore, that's all we got. So bx actually becomes 0. So you don't have any bx. So let's remove it. So at b, we only have a component of force in the y direction. And look, I said that one of the equations is going to be useless, guys. And that's going to be this guy, moment about z-axis. So notice that this equation is not going to give me anything because everything is sitting on the z-axis, all the forces, including the weight, which is parallel to z-axis. So I'm not going to get anything for that. All right, so now all I have to do is to go to my equations one by one, my force equations. So sum of the forces in x equals 0. I only have ax. Remember, bx became 0, and I removed it. So ax must be equal to 0. So let's remove that also. And then sum of the forces in y equals 0. So I have by, let me start with ay, and then I have by, which I've already calculated for you, right? And look, by is going in the negative direction, 37 and a half negative. So ay becomes what? 37 and a half, just like by, positive. So let's put it here also. Let's get rid of this. I actually get rid of this too. And I'm going to get to the AZ in a second. So I'll put AY equal 37 and a half. And then finally, in the Z direction, guys, we have what? Sum of the forces in Z equals 0. So what do we have? It's kind of, looks like it's gone, but it's there. Is A sub Z minus 100 equals 0. So A sub Z equal 100. So basically what this problem is trying to tell you that not much load in the Z direction is created at hinge B. That's why we neglected that in the statement of the problem. All right. So basically the burden of holding the weight pretty much is on hinge at A. So that's why we have the AZ. So AZ is equal to 100. So let me put that also here. Let's put it also in green, or I'll put it in red. All right. So AZ equal 100. So that's all we got basically for this story. So now, look, the interesting thing is the two green forces, AY and BY, they form a couple of what? 37 and a half times, you see the distance between them is 48. And you see that's balanced by what? The couple generated by these two forces, the weight, the 100, and this 100, A sub z. And the distance between them is what? That's the, that's the 24, right? Or 18, sorry, the 18 here. So that's going to be equal to what? 100 times 18. So that's it. Those are the type of reactions that we have acting on this source. So basically, two forces at hinge A, one in the Z and one in the Y, and then just one force in the Y direction at hinge B. Okay? So thanks for watching and listening. And as usual, guys, I appreciate if you could just hit the like key and like the video, and also subscribe to my channel. I'll always have new videos coming up, different topics, different subjects. Again, thank you and see you soon.